Introduction to Conventional Aerial Photography. In this video, we are going to see about Introduction to Conventional Aerial Photography. Aerial photography is taking the photographs of the ground from an elevated position. The term usually refers to images in which the camera is not supported by a ground-based structure. Platforms for aerial photography include fixed-wing aircraft, helicopter, unmanned aircraft systems, balloons, blimps and dirigibles, rockets, kites, parachutes, standalone telescoping, and vehicle-mounted poles. Mounted cameras may be triggered remotely or automatically. Handheld photographs may be taken by a photographer. The conventional aerial photography view of a place. This aerial photography must not be perplexed with air-to-air photo platform and subject. One of the most successful pioneers of the commercial use of aerial photography was by Sherman Fairchild, who started his own aircraft from Fairchild Aircraft to develop and build specialized aircraft for high-altitude aerial survey missions. Types of aerial photography. In this video, we are going to see about types of aerial photography. Aerial photography is several types. They are oblique, vertical, combinations, orthophotos. Photographs taken at an angle are called oblique photographs. If they are taken from a low-angle Earth surface aircraft, they are called low oblique, and photographs taken from a high angle are called high or steep oblique. Low-angle oblique of a building and high-angle oblique of a location. Vertical. Vertical photographs are taken too straight down. They are mainly used in photogrammetry and image interpretation. Pictures that will be used in photogrammetry are traditionally taken with special large format cameras with standardized and documented geometric properties. The vertical photography view of a house. Combinations. Aerial photographs are often combined. Depending on their purpose, it can be done in several ways, of which a few are listed below. Panoramas can be made by combining several photographs taken with one handheld camera. In pictometry, 5 rigidly mounted cameras provide 1 vertical and 4 low oblique pictures that can be used together. In some digital cameras for aerial photogrammetry, images from several imaging elements, sometimes with separate lenses, are geometrically corrected and combined to one image in the camera. The combinational photography view. Orthophotos. Vertical photographs are often used to create orthophotos alternatively, known as orthophoto maps. Photographs which have been geometrically corrected to be used as a map. In other words, an orthophoto is a simulation of a photograph taken from an infinite distance looking straight down. Perspective must obviously be removed, but variations in terrain should also be corrected for. Multiple geometric transformations are applied to the image, depending on the perspective and terrain corrections required on a particular part of the image. Orthophoto's map view of a town from high distance. Small format aerial photography. In this video, we are going to see about small format aerial photography. Small format aerial photography allows us to obtain large-scale and high-resolution images of the study areas. Pictures are taken with digital cameras suspended from kites and helium-filled balloons at flying heights of 100 to 900 meters. Depending on camera type and flying height, we are able to obtain resolutions of up to 7 mm per pixel. The small format aerial photography view of an area. The small aerial photography that is taken from kites with digital cameras. Aerial cameras. In this video, we are going to see about aerial cameras. Aerial photographs can be made with any type of camera, for example, 35 mm small amateur or 70 mm or special cameras that are purpose-built meant for mapping. There is many successful applications have employed aerial photography made from light aircraft with handheld 35 mm cameras. For the aerial study of large areas, high geometric and radiometric accuracy are required, and these can only be obtained by using cameras that are purpose-built. Aerial cameras are precision-built and specifically designed to expose a large number of films or photographs in rapid succession with the ultimate in geometric fidelity and quality expose. These cameras usually have a medium to large format, a high-quality lens, a large film magazine, a mount to hold the camera in a vertical position, and a motor drive. One of the smaller models of aerial camera, dated 1907, kept in Dutch Museum, Germany. Types of aerial cameras. Types of aerial cameras are aerial mapping camera single lens, reconnaissance camera, strip camera, panoramic camera, multi-lens camera, the multi-array camera, digital camera. Chemistry of film exposure. In this video, we are going to see about chemistry of film exposure. Photographic film is a strip or sheet of transparent plastic film base coated on one side with a gelatin emulsion containing microscopically small light-sensitive silver halide crystals. The sizes and other characteristics of the crystals determine the sensitivity, contrast, and resolution of the film. The emulsion will gradually darken if left exposed to light, but the process is too slow and incomplete to be of any practical use. Instead, a very short exposure to the image formed by a camera lens is used to produce only a very slight chemical change proportional to the amount of light absorbed by each crystal. This creates an invisible latent image in the emulsion, which can be chemically developed into a visible photograph. In addition to visible light, all films are sensitive to X-rays and high-energy particles. Most are at least slightly sensitive to invisible ultraviolet, that is UV light. Some special purpose films are sensitive into the infrared, that is IR region of the spectrum. In black and white photographic film, there is usually one layer of silver salts. When exposed grains are developed, the silver salts are converted to metallic silver, which blocks light and appears as the black part of the film negative. Photography of black and white picture. Color film has at least 3 sensitive layers. Dyes, which adsorb to the surface of the silver salts, make the crystals sensitive to different colors. Color film photography. Typically, the blue sensitive layer is on top, followed by the green and red layers. During development, the exposed silver salts are converted to metallic silver, just as with black and white film. But in a color film, the byproducts of the development reaction simultaneously combine with chemicals known as color couplers that are included either in the film itself or in the developer solution to form colored dyes. Because the byproducts are created in direct proportion to the amount of exposure and development, the dye clouds formed are also in proportion to the exposure and development. Following development, the silver is converted back to silver salts in the bleach step. It is removed from the film in the fix step. Fixing leaves behind only the formed color dyes, which combine to make up the colored visible image. There are several types of photographic film, including print film, color reversal film, black and white reversal film, film speed. Print film. In this video, we are going to see about print film. Print film, when developed, yields transparent negatives with the light and dark areas and colors, if color film is used, inverted to their opposites. This type of film is designed to be printed onto photographic paper, usually by means of an enlarger, but in some cases by contact printing. The paper is then itself developed. The second inversion, that results, restores light, shade, and color to their normal appearance. Color negatives incorporate an orange color correction mask that compensates for unwanted dye absorptions and improves color accuracy in the prints. Although color processing is more complex and temperature sensitive than black and white processing, the wide availability of commercial color processing and scarcity of service for black and white prompted the design of some black and white films which are processed in exactly the same way as standard color film. Print film of a photography from negative to a normal photo view. Color reversal film. In this video, we are going to see about color reversal film. Color reversal film produces positive transparencies, also known as diapositives, which are sometimes inspected with the aid of a magnifying loupe and a light box. If mounted in small metal, plastic, or cardboard frames for use in a slide projector or slide viewer, they are commonly called slides. Reversal film is often marketed as slide film. Large format color reversal sheet film is used by some professional photographers, typically to originate very high resolution imagery for digital scanning into color separations for mass photomechanical reproduction. Photographic prints can be produced from reversal film transparencies, but this process is usually more expensive and complex than printing from a negative. The example of color reversal film. Black and white reversal film. In this video, we are going to see about black and white reversal film. Black and white reversal film exists but is very uncommon. Conventional black and white negative film can be reversal processed to produce black and white slides. Although kits of chemicals for black and white reversal processing may no longer be available to amateur darkroom enthusiasts, an acid bleaching solution. The only unusual component which is essential is easily prepared from scratch. Black and white transparencies may also be produced by printing negatives onto special positive print film, still available from some specialty photographic supply dealers. In order to produce a usable image, the film needs to be exposed properly. The amount of exposure variation that a given film can tolerate while still producing an acceptable level of quality is called its exposure latitude. Color print film generally has greater exposure latitude than other types of film. The concentration of dyes or silver salts remaining on the film after development is referred to as optical density or simply density. The optical density is proportional to the logarithm of the optical transmission coefficient of the developed film. A dark image on the negative is of higher density than a more transparent image. Most films are affected by the physics of silver grain activation, which sets a minimum amount of light required to expose a single grain, and by the statistics of random grain activation by photons. The film requires a minimum amount of light before it begins to expose, and then responds by progressive darkening over a wide dynamic range of exposure until all of the grains are exposed and the film achieves, after development, its maximum optical density. Film speed. In this video, we are going to see about film speed. Film speed describes a film's threshold sensitivity to light. The international standard for rating film speed is the ISO scale, which combines both the ASA speed and the DIN speed in the format ASA/DIN. Using ISO convention film with an ASA speed of 400 would be labeled 400/27°. A fourth naming standard is GOST, developed by the Russian Standards Authority. See the film speed article for a table of conversions between ASA, DIN and GOST film speeds. Common film speeds include ISO 25, 50, 64, 100, 160, 200, 400, 800, 1600. Consumer print films are usually in the ISO 100 to ISO 800 range. Some films like Kodak's Technical Pan are not ISO rated, and therefore careful examination of the film's properties must be made by the photographer before exposure and development. ISO 25 film is very slow as it requires much more exposure to produce a usable image than fast ISO 800 film. Films of ISO 800 and greater are thus better suited to low light situations and action shots where the short exposure time limits the total light received. The benefit of slower film is that it usually has finer grain and better color rendition than fast film. Professional photographers of static subjects such as portraits or landscapes usually seek these qualities and therefore require a tripod to stabilize the camera for a longer exposure. A film with a particular ISO rating can be push-processed or pushed to behave like a film with a higher ISO by developing for a longer amount of time or at a higher temperature than usual. More rarely, a film can be pulled to behave like a slower film. Pushing generally coarsens grain and increases contrast, reducing dynamic range to the detriment of overall quality. Nevertheless, it can be a useful trade-off in difficult shooting environments if the alternative is no usable shot at all. The electromagnetic spectrum. In this video, we are going to see about the electromagnetic spectrum. The electromagnetic spectrum is the range of all possible frequencies of electromagnetic radiation. The electromagnetic spectrum of an object has a different meaning Instead, the characteristic of distribution of electromagnetic radiation emitted or absorbed by that particular object. The electromagnetic spectrum extends from below the low frequencies used for modern radio communication to gamma radiation at the short wavelength, high frequency end, thereby covering wavelengths from thousands of kilometers down to a fraction of the size of an atom. The limit for long wavelengths is the size of the universe itself. The short wavelength limit is in the vicinity of the Planck length. Most parts of the electromagnetic spectrum are used in science for spectroscopic and other probing interactions as ways to study and characterize matter. In addition, radiation from various parts of the spectrum has found many other uses for communications and manufacturing. Regions of the spectrum. In this video, we are going to see about regions of the spectrum. The types of electromagnetic radiation are broadly classified into the following classes: gamma radiation, X-ray radiation, ultraviolet radiation, visible radiation, infrared radiation, microwave radiation, radio waves. The notation EV stands for electron volts, a common unit of energy measured in atomic physics. A graphical representation of the electromagnetic spectrum. This classification goes in the increasing order of wavelength, which is characteristic of the type of radiation. While, in general, the classification scheme is accurate, in reality there is often some overlap between neighboring types of electromagnetic energy. For example, SLF radio waves at 60 Hz may be received and studied by astronomers or may be ducted along wires as electric power, although the latter is, in the strict sense, not electromagnetic radiation at all. For example, consider the cosmic microwave background. It was produced when matter and radiation decoupled by the de-excitation of hydrogen atoms to the ground state. These photons were from Lyman series transitions, putting them in the ultraviolet, that is UV part of the electromagnetic spectrum. Now, this radiation has undergone enough cosmological redshift to put it into the microwave region of the spectrum for observers moving slowly compared to the speed of light with respect to the cosmos. Radio waves. In this video, we are going to see about radio waves. Radio waves generally are utilized by antennas of appropriate size according to the principle of resonance, with wavelengths ranging from hundreds of meters to about 1 millimeter. They are used for transmission of data via modulation. Television, mobile phones, wireless networking, and amateur radio all use radio waves. The use of the radio spectrum is regulated by many governments through frequency allocation. Radio waves can be made to carry information by varying a combination of the amplitude, frequency, and phase of the wave within a frequency band. When EM radiation impinges upon a conductor, it couples to the conductor, travels along it, and induces an electric current on the surface of that conductor by exciting the electrons of the conducting material. This effect, the skin effect, is used in antennas. Microwave radiation. In this video, we are going to see about microwave radiation. The super high frequency SHF and extremely high frequency EHF of microwaves are on the short side of radio waves. Microwaves are waves that are typically short enough, measured in millimeters, to employ tubular metal waveguides of reasonable diameter. In a mobile phone, they are made by a transmitter chip and an antenna. In a microwave oven, they are made by a magnetron. Microwave oven. This effect is used to heat food. Low-intensity microwave radiation is used in Wi-Fi, although this is at intensity levels unable to cause thermal heating. Stars also give off microwaves. Microwave generators are commonly used in industry to cure chemical reactions, heat a part, or seal a plastic seam. This form of radiation is normally transmitted into the atmosphere from antennas like television antennas, FM radio antennas, and radar transmitters. Microwaves are also used by fixed traffic speed cameras and for radar, which is used by aircraft, ships, and weather forecasters. Infrared radiation. In this video, we are going to see about infrared radiation. The infrared part of the electromagnetic spectrum covers the range from roughly 300 GHz 1 mm to 400 THz 750 nanometer. It can be divided into three parts. Far infrared from 300 GHz 1 mm to 30 THz 10 micrometer. The lower part of this range may also be called microwaves. This radiation is typically absorbed by so-called rotational modes in gas phase molecules, by molecular motions in liquids, and by phonons in solids. The water in Earth's atmosphere absorbs so strongly in this range that it renders the atmosphere in effect opaque. However, there are certain wavelength ranges, windows, within the opaque region that allow partial transmission and can be used for astronomy. The wavelength range from approximately 200 micrometer up to a few millimeters, often referred to as sub-millimeter in astronomy, reserving far infrared for wavelengths below 200 micrometer. Mid-infrared from 30 to 120 terahertz, that is 10 to 2.5 micrometer. Hot objects, that is black body radiators, can radiate strongly in this range, and human skin at normal body temperature radiates strongly at the lower end of this region. This radiation is absorbed by molecular vibrations, where the different atoms in a molecule vibrate around their equilibrium positions. This range is sometimes called the fingerprint region, since the mid-infrared absorption spectrum of a compound is very specific for that compound. Visible radiation, that is light. In this video, we are going to see about visible radiation, light. The sun emits its peak power in the visible region, although integrating the entire emission power spectrum through all wavelengths shows that the sun emits slightly more infrared than visible light. By definition, the visible light is a part of the EM spectrum to which the human eye is the most sensitive. Visible light and near-infrared light is typically absorbed and emitted by electrons in molecules and atoms that move from one energy level to another. This action allows the chemical mechanisms that underlay human vision and plant photosynthesis. The light which excites the human visual system is a very small portion of the electromagnetic spectrum. A rainbow shows the optical visible part of the electromagnetic spectrum. Infrared, if it could be seen, would be located just beyond the red side of the rainbow, with ultraviolet appearing just beyond the violet end. Electromagnetic radiation with a wavelength between 380 nanometer and 760 nanometer, 400 to 790 terahertz, is detected by the human eye and perceived as visible light. Other wavelengths, especially near-infrared longer than 760 nanometer and ultraviolet shorter than 380 nanometer, are also sometimes referred to as light, especially when the visibility to humans is not relevant. White light is a combination of lights of different wavelengths in the visible spectrum. Passing white light through a prism splits it up into the several colors of light observed in the visible spectrum between 400 nanometer and 700 nanometer. Ultraviolet radiation. In this video, we are going to see about ultraviolet radiation. the amount of penetration of UV relative to altitude in Earth's ozone. Next in frequency comes ultraviolet UV. The wavelength of UV rays is shorter than the violet end of the visible spectrum but longer than the X-ray. UV in the very shortest range next to X-rays is capable even of ionizing atoms, greatly changing their physical behavior. At the middle range of UV rays cannot ionize but can break chemical bonds, making molecules to be unusually reactive. UV rays in the middle range can irreparably damage the complex DNA molecules in the cells, producing thymine dimers, making it a very potent mutagen. The wavelength of ultraviolet radiation rays from Sun. X-ray radiation. In this video, we are going to see about X-ray radiation. X-ray radiation appears after UV ray ranges, which, like the upper ranges of UV, are also ionizing. However, due to their higher energies, X-rays can also interact with matter by means of the Compton effect. Hard X-rays have shorter wavelengths than soft X-rays. As they can pass through most substances with some absorption, X-rays can be used to see through objects with thicknesses less than equivalent to a few meters of water. One notable use in this category in diagnostic X-ray images in medicine, a process known as radiography. X-rays are also emitted by the coronas of stars and are strongly emitted by some types of nebulae. However, X-ray telescopes must be placed outside the Earth's atmosphere to see astronomical X-rays. Gamma radiation. In this video, we are going to see about gamma radiation. After hard X-rays come gamma X-rays, which were discovered by Paul Villard in 1900. These are the most energetic photons, having no defined lower limit to their wavelength. Gamma rays are useful to physicists' ability and their production from a number of radioisotopes. Gamma rays are also used for the irradiation of food and seed, for sterilization, and in medicine. More commonly, gamma rays are used for diagnostic imaging in nuclear medicine, with an example being PET scans. Rectilinear propagation of light. In this video, we are going to see about rectilinear propagation of light. Rectilinear propagation of light is the tendency of light to only travel in straight lines. This means that if light crisscrosses between each other whilst going through a small hole, you will see the image upside down as the light goes straight up from down and down from up. In a homogeneous transparent medium, light travels in a straight line, and this is known as rectilinear propagation of light. This can be demonstrated by the following experiment. Experiment. Take 3 cardboards A, B, and C and make a pinhole at their centers. Place a burning candle on one side of the cardboard A and arrange the cardboards in such a way that the 3 pinholes and the candle flame are in a straight line. The candle flame will be visible through the pinhole of the cardboard C. Now slightly displace any one of the cardboards and try to see the flame through the pinhole of the cardboard C. The flame will not be visible. From this, it is clear that light travels in a straight line. This is one of the examples of rectilinear propagation. Specular reflection. In this video, we are going to see about specular reflection. Specular reflection is the mirror-like reflection of light or of other kind of wave from a surface in which light from a single incoming direction, a ray, is reflected into a single outgoing direction. In specular reflection, a mirror surface reflects a beam of light so that the angle of reflection is equal to the angle of incidence. For example, the angle of the incoming light is the same as the angle of the outgoing or reflected light. Diffuse reflection. In this video, we are going to see about diffuse reflection. A surface built from a non-absorbing powder such as plaster, or from fibers such as paper, or from a polycrystalline material such as white marble, reflects light diffusely with great efficiency. An illuminated ideal diffuse reflecting surface will have equal luminance from all directions which lie in the half space adjacent to the surface. Diffuse reflection is the reflection of light from a surface such that an incident ray is reflected at many angles rather than at just one angle, as in the case of specular reflection. Total reflection. In this video, we are going to see about total reflection. Total reflection is a phenomenon that happens when a propagating wave strikes a medium boundary at an angle larger than a particular critical angle with respect to the normal to the surface. When light is incident upon a medium of lesser index of refraction, the ray is bent away from the normal, so the exit angle is greater than the incident angle. Such reflection is commonly called internal reflection. The exit angle will then approach 90 degrees for some critical incident angle theta c, and for incident angles greater than the critical angle, there will be total internal reflection or total reflection. Refraction. In this video, we are going to see about refraction. Refraction is the bending of a wave when it enters a medium where its speed is different. The refraction of light when it passes from a fast medium to a slow medium bends the light ray toward the normal to the boundary between the two media. Demonstrate this phenomenon by a simple example. Consider a ray of light passing through the air and entering a plain parallel slab of glass. The relation between the angle of incidence θ1, the angle of refraction θ2, the refraction index of the glass slab N2 and the surrounding medium N1 sin θ1 is equal to N2 sin θ2. The angle of incidence and the refraction angle are the angles between the light beams and normal to the surface at the point where the beam crosses the interface. Absorption. In this video, we are going to see about absorption. The absorption of light occurs when a ray of light strikes a surface. The energy from the light is transferred to the surface material. The transfer creates heat, usually small amounts. An absorbing surface prevents reflection or diffusion of light striking on the surface. Atoms and molecules contain electrons. It is often useful to think of these electrons as being attached to the atoms by springs. The electrons and their attached springs have a tendency to vibrate at specific frequencies. Similar to a tuning fork or even a musical instrument, the electrons of atoms have a natural frequency at which they tend to vibrate. When a light wave with that same natural frequency impinges upon an atom, then the electrons of the atom will be set into vibrational motion. If a light wave of a given frequency strikes a material with electrons having the same vibrational frequencies, then those electrons will absorb the energy of the light wave and transform it into vibrational motion. During its vibration, the electrons interact with neighboring atoms in such a manner as to convert its vibrational energy into thermal energy. Subsequently, the light wave with that given frequency is absorbed by the object, never again to be released in the form of light. So the selective absorption of light by a particular material occurs because the selected frequency of the light wave matches the frequency at which electrons in the atoms of that material vibrate. Since different atoms and molecules have different natural frequencies of vibration, they will selectively absorb different frequencies of visible light. Wavelength and colors. In this video, we are going to see about wavelength and colors. Color is the visual perceptual property corresponding in humans to the categories called red, blue, yellow, green, and others. Color derives from the spectrum of light, distribution of light power versus wavelength, interacting in the eye with the spectral sensitivities of the light receptors. Color categories and physical specifications of color are also associated with objects or materials based on their physical properties such as light absorption, reflection, or emission spectra. By defining a color space, colors can be identified numerically by their coordinates. Because perception of color stems from the varying spectral sensitivity of different types of cone cells in the retina to different parts of the spectrum, colors may be defined and quantified by the degree to which they stimulate these cells. The wavelength ranges for colors. Temperature. In this video, we are going to see about temperature. The color temperature of a light source is the temperature of an ideal blackbody radiator that radiates light of comparable hue to that of the light source. Color temperature is a characteristic of visible light that has important applications in lighting, photography, videography, publishing, manufacturing, astrophysics, horticulture, and other fields. In practice, color temperature is only meaningful for light sources that do in fact correspond somewhat closely to the radiation of some blackbody. Color temperature is conventionally stated in the unit of absolute temperature, the Kelvin, having the unit symbol K. Color temperatures over 5000 Kelvin are called cool colors, bluish-white, while low at color temperatures 2700 to 3000 Kelvin are called warm colors, that is yellowish white through red. This relation, however, is a psychological one in contrast to the physical relation implied by Wien's displacement law, according to which the spectral peak is shifted towards shorter wavelengths, resulting in more bluish white for higher temperatures. Morphology. In this video, we are going to see about morphology. Color-coded images are used quite frequently in computer graphics. One might think of continuously colored images as temperature maps, where blue-colored pixels represent low temperature values and red-colored tones stand for high values. We do not refer to those types of images. Rather than that, we understand color-coded images as an image type in which each color embodies a semantic meaning. It should be pointed out that the distance of two colors in the RGB space does not necessarily correspond to their semantic relation. A field where we face color-coded images is in the area of classification applications, where raw data is processed by classification techniques to assign a semantic meaning to each pixel. Texture analysis 5, 10, satellite image analysis for land use classification 6, or medical image analysis for segmentation purposes of different tissue types are typical applications in that field. When classification tasks are solved with pixel-oriented approaches, one might get noisy result images due to misclassifications. Rods and cones. In this video, we are going to see about rods and cones. When light enters the eye, it first passes through the cornea, then the aqueous humor, lens, and vitreous humor. Ultimately, it reaches the retina, which is the light-sensing structure of the eye. The retina contains two types of cells: rods, cones. The outer segment of rods and cones. Rods handle vision in low light and cones handle color vision and detail. The rods, which are more numerous than cones, are responsible for our vision in dim light but don't function in bright light. Rods account for our night vision but cannot distinguish color. Our eyes are very sensitive at night but we don't see well straight in front of us. Cones are active at high light levels and allow us to see color and fine detail directly in front of us. The optics of the eye project an upside-down image of those objects on the rear, inner surface of the eyeball, that is, the retina. There, a dense carpet of light-sensitive photoreceptors converts light, that is, photons, into electrochemical signals, which are then processed by neural circuits in the retina and transmitted to the brain. Our peripheral vision is very good at detecting movement in a wide variety of illumination levels but is poor at low-resolution imaging and provides very little color information. The retinal layer, which covers most of the eye's inner chamber or visual system, is like a motion sensor with nearly 180 degrees of horizontal coverage. This motion detection has been useful to humankind for millennia and was once used as an early warning system for aggressors and for spotting game while hunting. Acuity. In this video, we are going to see about acuity. Visual acuity, VA, is acuteness or clearness of vision. Visual acuity depends on optical and neural factors, that is, the sharpness of the retinal focus within the eye, the intactness and functional of the retina, the sensitivity of the interpretative faculty of the brain. A common cause of low visual acuity is refractive error, that is, ametropia. How the light is refracted in the eyeball. Causes of refractive errors include aberrations in the shape of the eyeball, the shape of the cornea, and reduced flexibility of the lens. In the case of pseudomyopia, the aberrations are caused by muscle spasms. Too high or too low refractive error in relation to the length of the eyeball is the cause of nearsightedness, that is myopia, or farsightedness, that is hyperopia. Normal refractive status is referred to as emetropia. Other optical causes are astigmatism or more complex corneal irregularities. These anomalies can mostly be corrected by optical means such as eyeglasses, contact lenses, laser surgery, etc. Neural factors that limit acuity are located in the retina or the brain or the pathway leading there. A common impairment where the brain, that is primary visual cortex, is involved is amblyopia. In some cases, low visual acuity is caused by brain damage, traumatic brain injury, or stroke. When optical factors are corrected for, acuity can be considered as being a measure of neural well functioning. Visual acuity is typically measured while fixating, that is, as a measure of central or foveal vision for the reason that it is highest there. However, acuity in peripheral vision can be of equal or sometimes higher importance in everyday life. Acuity declines towards the periphery in an inverse linear, that is, hyperbolic fashion. Circle of confusion. In this video, we are going to see about circle of confusion. Circles of confusion is an optical spot of vaguely circular shape caused when a cone of light coming from a point source is not brought to a perfect point focused by a lens system. One reason there might be a circle is that lens is not focused. Even when the lens is focused, though, there will always be a circle of confusion of some shape and size. The circle will really be the shape of the opening in the aperture, and additionally, no lens is capable of perfect operation, although modern manufacturers go to extremes to get as close as possible. The best a lens can do is called the circle of least confusion. The good thing is that if the circle is small enough, we don't notice it. In fact, that's how depth of field is defined. It's the range of distances for a particular setup of a camera for which the circle of confusion is too small for us to notice. In a minute, we will talk more about what too small to notice means. You need to know the COC for your camera to figure out the depth of field for a given focal length, aperture, sensor size combination. Persistence of vision. In this video, we are going to see about persistence of vision. Our eyes offer one of the 5 specialized means by which our mind is able to form a picture of the world. The eye is a remarkable instrument having certain characteristics to help us process the light we see in such a way that our mind can create meaning from it. Take the motion picture, the scanning of an image for television, and the sequential reproduction of the flickering visual images they produce. These work in part because of an optical phenomenon that has been called persistence of vision, and its psychological partner, the 5 phenomenon, the mental bridge that the mind forms to conceptually complete the gaps between the frames or pictures. Whenever light strikes the retina, the brain retains the impression of that light for about 10th to 15th of a second, depending on the brightness of the image, retinal field of view, and color after the source of that light is removed from sight. This is due to a prolonged chemical reaction. As a result, the eye cannot clearly distinguish changes in light that occur faster than this retention period. The changes either go unnoticed or they appear to be one continuous picture to the human observer. When we go to the movies, we know that a motion picture creates an illusion of a constantly lit screen by flashing individual photographs in rapid succession. Even though the movie screen appears to be constantly lit, it is, in fact, dark part of the time. It was the flickering image on the screen that gave rise to the term flicks in the early days of movies. Today's motion pictures flash images on the screen at 24 frames per second or 48 in that each frame is flashed twice for a flicker-free picture. American television actually transmits and recreates 30 complete images per second to give the illusion of a single continuous picture. Parallax and perspective. In this video, we are going to see about parallax and perspective. Parallax is a displacement or difference in the apparent position of an object viewed along 2 different lines of sight and is measured by the angle or semi-angle of inclination between these 2 lines. Astronomers use the principle of parallax to measure distances to the closest stars. Here the term parallax is a semi-angle of inclination between 2 sight lines to the star, as observed when the Earth is on opposite sides of the Sun in its orbit. These distances from the lowest rung of what is called the cosmic distance ladder, the first in a succession of methods by which astronomers determine the distances to celestial objects, serving as a basis for other distance measurements in astronomy, forming the higher rungs of the ladder. Parallax also affects optical instruments such as riflescopes, binoculars, microscopes, and twin-lens reflex cameras that view objects from slightly different angles. Many animals, including humans, have 2 eyes with overlapping visual fields that use parallax to gain depth perception. This process is known as stereopsis. In computer vision, the effect is used for computer stereo vision, and there is a device called a parallax rangefinder that uses it to find range and in some variations also altitude to a target. To understand parallax using a real-world example, imagine that you are a passenger in a moving car looking through the windows at the buildings and trees alongside the road. As the car moves, the trees closest to you appear to travel through your field of vision much faster than do buildings in the far distance. A simple everyday example of parallax can be seen in the dashboard of motor vehicles that use a needle-style speedometer gauge. When viewed from directly in front, the speed may show exactly 60, but when viewed from the passenger seat, the needle may appear to show a slightly different speed due to the angle of viewing. Photography versus human eye. In this video, we are going to see about photography versus human eye. Our eyes are capable to look around a scene and dynamically adjust based on subject matter, whereas cameras capture a single still image. This trait accounts for many of our commonly understood advantages over cameras. For example, our eyes can compensate as we focus on regions of varying brightness, can look around to encompass a broader angle of view, or can alternately focus on objects at a variety of distances. However, the end result is akin to a video camera, not a stills camera that compiles relevant snapshots to form a mental image. A quick glance by our eyes might be a fairer comparison, but ultimately, the uniqueness of our visual system is unavoidable. Angle of view. In this video, we are going to see about angle of view. With cameras, this is determined by the focal length of the lens along with the sensor size of the camera. For example, a telephoto lens has a longer focal length than a standard portrait lens and thus encompasses a narrower angle of view. Unfortunately, our eyes are not as straightforward. Although the human eye has a focal length of approximately 22 mm, this is misleading because the back of our eyes are curved. The periphery of our visual field contains progressively less detail than the center. Each eye individually has anywhere from a 120 to 200 degree angle of view, depending on how strictly one defines object as being seen. Similarly, the dual eye overlap region is around 130 degree or nearly as wide as a fish eye lens. However, for evolutionary reasons, our extreme peripheral vision is only useful for sensing motion and large-scale objects such as a lion pouncing from your side. Resolution and detail. In this video, we are going to see about resolution and detail. Most current digital cameras have 5 to 20 megapixels, which is often cited as falling far short of our own visual system. This is based on the fact that at 20 by 20 vision, the human eye is able to resolve the equivalent of a 52 megapixel camera, assuming a 60 degree angle of view. However, such calculations are misleading. Only our central vision is 20 by 20, so we never actually resolve that much detail in a single glance. Away from the center, our visual ability decreases dramatically such that by just 20 degrees off center, our eyes resolve only 1/10 as much detail. At the periphery, we only detect large-scale contrast and minimal color.